So it's my great pleasure to introduce Iskander Taimanov from the Russian Federation, and he will tell us about surfaces with spinors and Soliton equations. Please go ahead.
Okay, I would like to speak on the subject which lies on the border of surface theory and integrable systems of mathematical physics. First, I will start with the classical definition of the first fundamental form of the induced metric of a surface immersed into Euclidean n space. If R is the immersion of the surface, and here is D is domain in R2 with the coordinates U and V, the induced metric is just a quadratic form which corresponds to tangent vectors to the surface, their lengths in the ambient space. If you do have such a form, you would like to have some better better forms, in better views. You have to probably to work with special coordinates or with which it's easier to do computation for different problems. For instance, if you would like to study the negatively curved surfaces in R3, it's worth to introduce asymptotic coordinates. For general surfaces, we can introduce conformal coordinates. They say that the coordinates U and V on the surface are conformal if the induced metric is diagonal. It means it's proportional to the Euclidean metric. Conformal coordinates were introduced by Gauss, who proved the existence for real analytical surfaces. And he did it for some special reasons. He had been working in cartography and were looking for best charts for the pieces of the surface of the Earth, for some special pieces of the territory which could be applied for different reasons. And he looked for coordinates which respect angles between lines, and for coordinates which distort lengths of lines in the controlled way on sufficiently large pieces of the surface. And actually he introduced that. Now it's called the conformal Gauss projection or the Gauss-Kruger projection, which is very important in cartography. But he did that in 1820s. At the time, that was only the rise, the emergence of the complex analysis. And it appeared that if you would write down these conformal coordinates in terms of conformal parameter Z, which is just U plus EV, the U and V are conformal coordinates, that enables us to apply to surface theory the strong machinery of complex analysis. That was done later, not by him, but that appears to be very efficient. For many surfaces, the derivation equations are reduced to the Cauchy-Riemann equations for certain quantities. It's classical Cauchy-Riemann equations. That allows to describe the surfaces locally in terms of some holomorphic data, and that stands behind the effectiveness of integrable systems theory and surface theory. Actually, these surfaces are called integrable surfaces. So that's a very important point in the integrable systems. Moreover, surface theory was one of the origins of theory of integrable systems. First time such an integrability manifested itself in the Weierstrass representation of minimal surfaces. Yes, surfaces with vanishing mean curvature. This is the formulas of a Weierstrass representation introduced in early 1860s. Assume we do have two holomorphic functions, psi1 and psi2 bar. Then this formula gives a minimal surface in R3 with zero conformal parameter. Here, what does it mean? We have a fixed point P naught, map it into some point into R3, and then take the integrals in the left-hand side along some paths which join P0 and P. For uniqueness, let us assume that the surface is simply connected. Otherwise, we shall work with the covers of the surface. Then we do have a minimal surface locally. Small domain is simply connected. We do have every minimal surface, and we do have every minimal surface even globally. So many problems of minimal surfaces are reduced to problems of complex analysis, but the global problems assume that we would like to look for embeddedness of the surfaces. We have to be careful that there are no periods, there are no lines for which these integrals, which join two different points on in domain D, and for which all these integrals vanish. So that's another complicated problem. So if we would like to solve the problem locally, you can describe minimal surfaces in terms of holomorphic data, Psi1 and Psi2 bar. If you would like to do some global analysis of these surfaces, that's a hard problem. And actually, this is a generic feature, a general feature for all integrable surfaces. So locally, they are described in terms of holomorphic data, and globally, it needs a hard work, which is not done for many cases. And that's additional story. But integrability just means a local description in terms of some holomorphic data. I'm starting with now a theorem by Konopelchenko, a physicist who was at this time in Novosibirsk as myself, and now he's in Italy. He moved in Italy in the middle of 1990s, and he proved the following: let psi be defined in some, for simplicity, a contractible domain, simply connected domain, and it meet the Dirac equation d psi equals 0, where psi is the vector function psi1, psi2 with such entries. And D is the two-dimensional Dirac operator with the real valued potential U. This is two-dimensional, this is free operator, 0 D minus D bar 0. The D here, this is means the derivation with respect to Z, and D bar is derivation with respect to Z bar. And U is some real valued potential, which is defined in this domain D. Then the Weierstrass formula determines a surface in a free with Z a conformal parameter. For U equals 0, we have the Weierstrass representation of minimal surfaces. So this is just a generalization. The induced metric takes the form d squared is some conformal factor dz dz bar. That means that dz is a conformal parameter. The square root of this conformal factor is just the sum of the squared modulus of psi1, psi2 entries of these functions. And the potential U of Dirac operator equals to h, the square root of conformal factor, divided by 2. The h is the mean curvature. So h, then h vanishes. We have a zero potential. We do have minimal surface. And this is just the generalization of this, of the Weierstrass formula for this case. This theorem was derived from the similar formula in the book of a treatise of differential geometry of curves and surfaces by Eisenhardt. It's problem 35.4, where instead of the Dirac equation, he used the following condition. So Eisenhardt used the second order scalar differential operator, for which psi1 and psi2 bar lies in its curve. But the book was published at the beginning of 20th century. It's unclear, did Eisenhardt prove that himself, or did he quote some article? Because as you look on some his other books, you see that some problems, especially in his introduction to Riemannian geometry, he put problems with the names of the authors for whom this solution of these problems were results of their original mathematical works. For instance, that happens with Ricci. A lot of results of Ricci were introduced by as problems in the introductory book to Riemannian geometry. Probably Eisenhardt took it from some other paper. That's, I don't know. But this operator L is not very good, because it assumes that U, okay, not vanishing everywhere, but you have zeros somewhere. then the operator has singular coefficients. Moreover, we can notice that D can be written down as the square root of the Schrodinger operator. So that's original. So Dirac operator is the square root of the original Dirac operator in mathematical physics is the square root of the Klein-Gordon operator. Now it's the square root of Schrodinger operator. So this condition by Eisenhardt can be written in this form of this Dirac equation, d psi equals 0. And that was done in the article by Konopelchik in Used Surfaces and the Integrable Dynamics, which was published as preprint of Butker Institute of Nuclear Physics in 1993. I picked up this quote because the article itself was published much later, 3 years later in the journal. But so that I would like to kind of point the beginning of the story for myself, at least. It appears that also this representation is equivalent to representation of Kinmotsu. For surfaces with prescribed mean curvature, but operators which were coming in the Kinmotsu representation also may have singularities in their coefficients. I was told that for special CMC surfaces, similar representation were kind of only for CMC surface, constant mean curvature surface, were given by Abrish on his lectures. But here, I would like to say why Konopelchik introduced his representation, his formulas. There is the modified Novikov-Veselov equation. This is Soliton equation, integrable systems from Soliton theory, 2 + 1 dimensional. So which has this form. And in the limit that U depends on only on one parameter, it reduces to modified Korteweg-de Vries equation. It is represented as LAB triple. So dt d over dt is equal commutator dA minus bd. So the L stands for d, and A and B are matrix differential operators. So you see, if B vanishes, when we do have the famous Lux pairs, this is a classical representation for one-dimensional integrable systems. This representation was introduced by Monakov for 2 + 1 dimensional systems because reasonable systems with 2 + 1 dimensional operators do not admit Lux representation. So only trivial cases do appear. But what is the similarity with the Lux representation? The similarity is the following. The evolution deforms the zero energy level of eigenfunctions D, as in the case of Lux representation. But that's only valid for the on the zero level energy. If d psi equals 0, but there are in this 2 + 1 in this two-dimensional operator there are plenty of such functions, then starting with psi, which satisfies this equation, d psi over dt plus 8 psi equals 0. The A's differential operators where coefficients depends on U and V also and their derivatives. I do not write it here for brevity. Then at any moment of time, the solution, fixed moment of time, the solution of this equation again would satisfy this equation d psi equals 0, if such a solution do exist. Deformation means the following. We take the surface gamma naught, which is constructed from some function psi at the zero moment of time, and then take the solution of modified this equation, modified Novikov-Veselov equation with this Soliton, and start to deform psi corresponding to this solution. Then at any moment of time, we do have the surface gamma t, which is determined by the Weierstrass formula up to translation periods by this spinor psi at this moment t. I already called psi spinor. Why that? Because it appears that every surface in A3 with a fixed conformal parameter 0 admits the spinor representation globally. What means spinor representation? We have to construct such a representation of the, for instance, for closed surface. So psi cannot be a function of it. It has to be a section of some bundle, which appears to be a spinor bundle. What is the most interesting in that the form u squared dx dy is globally defined. its integral of the surface is proportional to the Willmore function. So the Willmore function deviates the squared norm, evaluates the squared norm of the deviation of the free Dirac operator with u equals 0 from the free Dirac operator of the given Dirac operator which comes into representation. So this point appeared to be the most interesting for me. And moreover, it appears that if we consider the Konopetchenko deformations of the tori, this deformation evolves tori into tori and preserves their conformal classes and the values of the Willmore function. I published this article in some text in some collection of papers published by American Mathematical Society, which is unavailable in internet. It was published a few years ago, but originally this text appears in archive. This is the reference to it. And so I given the second reference just for this reason, because to make it, to show that it's available electronically. And now I'm going to discuss the possible application of this Spinor representation. It would be interesting to apply this representation to open problems in surface theory. For instance, bending of surfaces, or the Carathéodory problem on the existence of at least 2 umbilicus on spheres in R3. This problem is solved for real analytic surfaces, but it strongly uses that the surface is real analytical. In terms of Weierstrass representation, it means that if we assume that there is just one umbilic, we can put it at infinity, represent 2-dimensional sphere as 2-dimensional plane compactified by the infinity point, and look for some solutions of the Dirac equations with the condition that there are no umbilics inside. This condition is written in terms of some equation of psi, a quadratic equation of psi and derivatives of psi, and the condition on some growth of psi. I looked briefly on this problem and didn't go further because that was not the point for me at this moment. Also, another interesting case, if some conjecture appears to be false, such a representation may help in constructing explicit counterexamples. For instance, that was done by Abrish, and he constructed first visible counterexamples to the Hopf conjecture. Disproved by Venter, who proved that there are CMC tori immersed into R3, and Abrish constructed CMC tori in explicit formulas. And actually, he was one of the persons who involved me into this subject because he was my close friend. The Willmore functional and the Dirac operator. That's an interesting point, which was probably the most interesting for me in this representation. So that's the Willmore function, as already said, measures the squared integral deviation of the Dirac operator corresponding to the surface representation from the free operator. Hence, for closed surfaces, the lower bounds for the Willmore functional show how strong has to be such a deviation to convert a non-compact minimal surface into a closed one. So you don't have minimal surfaces, it's never compact, even complete. You take small deviations of this free operator, small values of u, and still looking for this integrable form is still not compact, but how strong has to be deviation? This is a kind of physical explanation of such lower bounds. The most classical problem concerning the Willmore conjecture was the Willmore function was the Willmore conjecture, which reads that the minimum of the Willmore function among tori and R3 is attained at the Clifford pros. And it was proved in a very fabulous paper by Marcus and Neves, who used the regularity theory of minimal surfaces and calculus of variations. In the middle of the 90s, we proposed an approach to proving it that was based on the Spinor representation integrable systems theory. And I briefly say about that. This approach was not implemented due to analytical difficulties related to the spectral theory. At the beginning, I thought that that would help. But it appears there are some complicated problems related to the rhythm deformation of spectral curves. It was based on the following, our conjecture, which still may be helpful to establishing the lower bounds for the Willmore function in different conformal classes of tori. Because you see the modified Novikov-Veselov law respects conformal class. A torus non-stationary with respect to the modified Novikov-Veselov law cannot be a local minimum of the Willmore function. Otherwise, the minimum has to contain an infinite family of tori invariant under this flow. If this flow is not reduced to some conformal deformation, because you know that the Willmore functional is conformally invariant. So it's a real non-trivial deformation. And such degeneration of the minima is very unlikely. That was the argument. By the general philosophy of integrable system, the stationary solution of the modified Novikov-Veselov equation has the simplest possible spectral curve. The spectral curve is an analytical variety which parameterizes all Floquet functions psi of d such that d psi is equal to 0. We recall here that the Floquet functions for every differential operator, two-dimensional differential operator, I shall speak now at two-dimensional, but that's the definition is valid in all dimensions, with double periodic coefficient is a solution of this equation, d psi equal psi for some constant e, which is double periodic up to multiplications by constants corresponding to the periods of potential E. This is the Floquet, or physicists call this function Bloch functions, and they are very important in mathematical physics. The spectral curve is preserved by the Soliton flow. So this is actually the first integral of the flow, the whole spectral curve. The Willmore function is encoded in this spectral curve. So it's, and for Clifford torus, the spectral curve is a rational curve with two double points. So it's very simple. But okay, to reduce the Willmore conjecture to these conjectures about spectral curves, was impossible at this time. Now I would like to look for other applications, what I did at this time. For instance, the kernel of D admits the symmetry. This is non-trivial symmetry, it's anti-involution, and hence its dimension is always E. Looking for the estimates for the Willmore functional from below, I proved the following. For spheres which has a spinor representations with a one-dimensional potential, U depending on ln x, the Willmore functional is greater or equal than 4 pi n squared, where the kernel, dimension of the kernel is 2n, and the equalities are achieved at the Soliton potentials. What are the spheres with one-dimensional potentials? These are, for instance, spheres of revolution, but there are many others. This theorem was proved by using mathematical physics, the inverse scattering method, in particular the Marchenko equation from this method. I would like to mention that 5 days ago, Marchenko celebrated his 100th birthday. He introduced this equation in the 50s. We conjectured that this inequality, Willmore functional greater or equal 4 pi n squared, holds for all spheres. But the inverse scattering method for two-dimensional potentials is not well developed, and we couldn't do that by means of mathematical physics. Soon after this conjecture appeared on some school, summer school in Berlin, Friedrich showed that this conjecture implies the following state. Given an eigenvalue lambda of the Dirac operator D on a two-dimensional spin manifold homomorphic to the two-sphere, we have the following equal lambda squared multiplied by area of M greater or equal P M squared lambda. The M lambda is the multiplicity of lambda. Such an equality was already known for M lambda equal 2. It was proved by Christian Baer. What was the argument by Friedrich? On a spin manifold of dimension 2 with a metric, the given metric, which already we mentioned, exponent to alpha dz bar. This is the metric of the Weierstrass or the induced surfaces, surface constructed by Weierstrass representation. The Dirac operator takes this form, and the equation d phi equal lambda phi is rewritten exactly in the form of Dirac equation of the Weierstrass representation. It's two-line derivation. Here we had Here the psi is equal exponent alpha over 2 phi. And if lambda is constant, we have the proof of the Friedrich statement. This is the proof. The other way around, if lambda is equal h, then this is exactly the Dirac equation of the Spinor-Weierstrass representations. Sin exponent alpha is the squared norm of psi. We have the norm of phi is equal 1, and therefore the Weierstrass representation is written in terms of solutions of the Dirac equation d phi equal h phi of constant length. 1. That was done by Friedrich. This argument led to a generalization of the Spinor-Weierstrass representation to the so-called spinor representation of immersions of manifolds, which are not necessarily two-dimensional, into certain homogeneous spaces. Of course, the Weierstrass or Willmore functional is generalized to the spinor energy of these representations. But since I was mostly interested in the interrelation between surface theory and spectral theory of operators, I didn't follow this subject myself. I only shall say that there are well-developed theory of it. And the conjecture of mine was proved by Ferus, Petit, Leshkin, Pinkal by a very nice argument. Then they use so-called quaternion algebraic geometry. They consider this Dirac operator as a kind of Debye operator in quaternionics bundles, and Debye operator was also some potential. And just the analog of the Plücke formula from algebraic geometry enables them to prove in the first line for spheres just inequality, which was conjectured by myself. And they proved it even for surfaces of higher genera. For tori, it appears there are two different cases. Then n is even and n is odd. In the first case, it's for pi n squared over 2. In the second, pi n squared minus 1 over 4. Yes. And this is in the last line, you see the inequality, which was proved for surfaces of genera greater than 1. The quaternion algebraic geometry, which was developed from the base of this representation of surfaces, enables us to construct very interesting transformation of surfaces, kind of Darboux transformation and so on, and also helps to resolve some problems of surface theory. What was the most interesting for me at this point that they started to look for surfaces in R4, not in R3. And what is the Weierstrass representation surfaces or surfaces in R4? Let's consider two Dirac operators, D with the complex valued potential and the joint operator, for which these potentials on diagonals are swapped. Here it's for D it's U bar, for D P it's U bar U. And take two, let us say, spinors again, psi and phi, which meet the pair of Dirac equations. D psi equals 0, dv phi equals 0. Then there is this similar formulas for immersion of surfaces in R4. I'm writing it my own manner because I shall use this form later. S is a surface in R4, where R4 is identified with the space of quaternions. For U real valued and psi equal phi, it reduces to spinor representation of R3. These explicit formulas were written down again by Konopelchenko, but in 2000, who followed the ideas of Pinkal and his collaborators. They started to consider surfaces in R4, but in non-coordinate language. Now we have to explain why these dimensions 3 and 4 are exceptional for this case. You see, just by simple computations, the parameters unit surface in Rn is conformal on it if and only if this quadratic equation holds. This is just straightforward. calculation. Then tuple of these derivatives of coordinates in Z taken up to multiplications by a non-vanishing context defines the tangent plane to the surface. Because the real and part of this vector and the imaginary part of this vector, these are two orthogonal vectors. They are orthogonal with respect due to the first equation, and they give you a basis. The multiplication by non-vanishing constant give you just rotations of these bases, and also multiplying of this undulations of this basis. And these two vectors are the same length. It also follows from this quadratic equation. And now take a point on the quadratic Q, which is defined to Cpn minus 1. This is the quadratic. It's defined on the range of two plane, as I already said on the example of this Gauss map. It is spanned by this vector, real and imaginary part of this vector. Therefore, for a surface in Rn with a conformal parameter Z, the Gauss maps takes this form. It's just the Z, we're mapping Z into the point of the quadratic Qn, such that the homogeneous coordinates of the quadratic are given by derivatives of coordinates with respect to conformal parameter. So this is a very nice formula for the Gauss maps in terms of conformal parameter. We know that the Gauss map for surfaces in R3 takes the values in the two sphere, in the unit two sphere. And that's actually the case. For n equal 3, Q3 is diffeomorphic to CP1. There, this mapping. This mapping is well known, for instance, in number theory, because if you put a right-hand side to the if they take the squares of these three quantities, you get the solution of the equation x squared by y squared by z squared equals 0. Since the first x squared is purely imaginary, we can move it into the right-hand side. So we do have the parameterization of solution of the equation x squared plus y squared equals z squared. So that's but this means that A and B are homogeneous coordinates on CP1, which parameterizes the Grassmannian. For n equal 4, we have the Segre mapping, CP1 times CP1 into Q4. This is again diffeomorphism. And you see this, these A and B are exactly psi1, psi2. Here that's A1, A2, it's psi1, psi2 bar, B1, B2, phi1, phi2 bar. And here it's again psi1 for surfaces in R3, A is psi1 and B psi2 bar. So this is the case. For other dimensions, this Grassmannian doesn't have this such a good rational parameterization. So this is special cases of dimension 3 and 4 when we can parameterize the Grassmannian by rational curve and by the points from the square of the rational curve CP1. This is exactly the form of the spinors which I mentioned above. But in difference with three-dimensional case, the spinors reconstructed by the surface as up to multiplication plus minus 1. For surfaces in R4, it's reconstructed up to the gauge transformations, where H is holomorphic. And that enables us to prove the existence of Weierstrass, of spinor representation of surfaces in R4. When we take the universal covers of these representations, take this solution of this Dirac equation, and using this gauge transformation, show that we can show that there is such a solution which converts into the immersion of the closed surface. And now I'm coming to the Davy-Stewartson equation, which appears in hydrodynamics. It's as a modified Novikov-Veselov equation. It has a representation by some L/B triple. It's called the focusing Davy-Stewartson equation. The only point that this operator, Dirac operator, which is common in its representation, is the Dirac operator which comes into representations of surfaces in R4. And another point, that this equation in difference with modified Novikov-Vasilov equation has a physical meaning because it was originally introduced in hydrodynamics in early 1970s. Following his previous trick, Konopelchenko proposed to construct Soliton deformation of the same surfaces in the same manner, completely the same manner. We take the deformation of psi, take the deformation of phi, which are governed by the differential operators A and AB, matrix differential operators where coefficients depend on U and V. So such deformation also depends on resolving this constraint. That's important. And as I had shown, that one can define deformation governed by DS2 globally such that it preserves the Willmore function. It's again the Willmore function. It's the squared. It's the squared norm of U. Here, potential U is a complex valued, so I have to put into the modulus. It's up to the Willmore function of the surface. So this is the first integral. And now I would like to use this representation the other way around. First, I would try to apply it to surface theory to relate the conformal geometry of surfaces to spectral properties of differential operator D, which comes into this representation. And now let us do the other way. We apply the surface theory to constructing solutions of these equations, blowing up solutions with interesting types of singularities. There is so-called theory of Muttard-Darboux transformations, which are widely used in mathematical physics for constructing explicit solutions of differential equations or constructing the explicitly basis of some solvable models, solvable differential operators. For instance, the classical Darboux transformation for one-dimensional operator, Schrödinger operator, was used by Dirac in his book Principles of Quantum Mechanics. And by means of this transformation, he computed the spectrum of the harmonic oscillator. This is in his book. And the Muttard transformation is the original transformation introduced by Muttard for two-dimensional case, actually for solving problems in surface theory in 19th century. It is a purely analytical. But now we're working with not with one-dimensional Schrödinger operator as Dirac did, but the two-dimensional Dirac operator. And for it, we have the following transformation. Assume that the Dirac operator comes into representation of some surface, and S is this surface. Then we take the inverse of S, just inverse of this matrix. It's just the Möbius transformation. Of course, we have to compactify R4 by infinity because the origins of R4 is mapped into infinity. So we have a surface in S4. It is conformal because it's Möbius transformation. And hence we get transformation of potentials. Moreover, if original potential U satisfies the Davy-Stewartson equation, then the transformed potential also satisfies the Davy-Stewartson equations. The formulas are quite long and complicated. Analytical formulas of U tilde are quite long. But the geometrical picture behind these formulas is very simple. We are just take the family of surfaces U evolving due to this Davy-Stewartson equation, and at every moment of time invert them. What happens if the surface will go through the origin? This means that origin will be mapped into infinity, and U potential would gain a singularity. So it's the way to construct singularities of solutions to Davy-Stewartson equation. The simplest way to start with, we have to have initial family of surfaces. And for that, it's better to do some integral cases. These are minimal surfaces in R4. U is equal to 0. The simplest examples of minimal surfaces R4 is given by the graph. Z2 equals FZ1, where R4 is identified with the two-dimensional complex space, and F is holomorphic functions. Then this function U is actually the resultant. So we have the this minimal surface. it has to move. So for moving it, we have to assume that f depends on the parameter t and satisfies this equation, df over dt equal y and the square root of f, square derivative in z. And then after Möbius transformation, they get this potential, which again satisfies the Davy-Stewartson equation. There are a couple of examples. For instance, this one, starting with f z squared minus 2i t minus c, the c is real valid. We have this solution with a terminal time has an indeterminacy of this form, indeterminacy in 1 point. Nevertheless, it's phase decaying outside this point. U belongs to L2. The corresponding spinor has this form. It has a singularity at the moment then t equals c. But we have the know that u is the first integral. What happens with the first integral u? It jumps. When we're going through the origin, it's failed by 2 pi. Originally, it's 2 pi. It becomes pi, and then the solution gains the regularity, and it returns to pi. So the existence of such a first integral doesn't help us in proving the regularity of this solution. So this is an example. So this is another example. It's very similar. What I would like to say, in both examples, the value of squared normal of potential u is a multiple of pi. Why? It's because the surfaces S-1 are immersed branched Willmore spheres. And the Willmore functional for for spheres is quantized. Its values are multiples of pi. What is another point which I would like to stress? At the terminal time, the spinor psi gains singularity, and therefore the zero levels discrete spectrum of D is not preserved. It's in difference with Lux space that the discrete spectrum is preserved, and that's actually used in the inverse scattering solution method for solving the KdV equation and some other. Analogous effects were found by means of the Mutar type transformation bias for the Novikov-Veselov or modified Novikov-Veselov equations. And that demonstrates a mechanism of blow-ups of solutions to Soliton equation represented by L by triples, which is related to the non-conservation of the zero-level discrete spectrum of L operator. So it looks these are related mechanisms, related situation. Of course, I would like to notice that there is another solution, famous as our solution for the same equation, another time of blow-up, which is stable. This is not stable. You see from the formulas, a small deformation of the initial data destroy the appearance of singularity. But this Ozawa solution cannot be obtained by this by means of surface theory. That's what I wanted to say in my talk, and I would like to thank you for your attention.
Okay, thank you very much, Iskander, for this nice talk and all the aspects of, maybe I should call it the generalized Dirac Weierstrass representation of surfaces in R3 and R4. Very beautiful. So I think with that, thank you, and we end the session. Thank you.
Thank you. Bye.